Can you say again? I couldn't hear you.
Oh, yeah, I'm ready.
Oh, good. Okay, great. So, yeah, our next speaker is Peter Rindal. We are very happy to have him. He was a student at Oregon State, and now he's a researcher at Visa Research. He has done a lot of work on sort of applied cryptography, specifically sort of multi-party computation and homomorphic encryption, and and he'll tell us about all the work that he did on sort of efficient private set intersection from homomorphic encryption. So take it away, Peter.
Yeah, thanks. Yeah, this is sort of work that came out of grad school. I was working on private set intersection, and then Kim Lane hosted me for an internship at Microsoft, and they were doing a bunch of FHE work. And so we sort of merged our two where our headspaces were. And this is sort of the work that came out of it. And Zico also helped. And he was at university at the time. Okay. Okay, so most of you probably know what private set intersection is, but if you don't, it refers to the problem of typically with two parties, each holding a set X and Y, and they wish to learn the intersection of the sets without revealing any additional information about their sets themselves. In particular, we'll consider the scenario where there's a sender party and a receiver party. Each possess a set, and the receiver should learn the intersection of the set. But they shouldn't learn any additional information about X, and the sender shouldn't learn anything at all. So this is sort of the ideal functionality that we are aiming for. And throughout this talk, I'll use this diamond notation to refer to that kind of ideal functionality. And we consider this the classic real-world ideal world scenario where we have a figurative trusted third party that computes this function for us. But in reality, the parties actually will be sending messages back and forth. And we'll consider two types of parties. Some can be semi-honest, and basically what this means is they'll send the correct messages during the protocol. We'll first construct a semi-honest protocol, and then later we will consider malicious security, where one or both the parties will arbitrarily deviate, and then we'll see what type of guarantees we can achieve in this setting. But first, let's consider some of the motivating applications for why we'd want to do private set intersection. Maybe one of my favorite applications is actually being used in the wild by Google. And here, Google has some, say Tesla signs up to advertise their cars on Google. And so Google shows the advertisement to some set of users. And then Tesla, on their hand, sees that they have some set of customers that came in and actually bought a Tesla in the store. And now you'd like to be able to correlate who saw the ad and came in and bought the Tesla, so that you could sort of get some sort of idea about how effective the advertising is. And the challenge is here is that neither of these parties are really willing to share their customer information with the other. And so you sort of get into a sticking point. And so here you could run private set intersection between the two sets, and sort of only the customers that saw the ad and bought the car are revealed. And what's more, Google actually does something a little bit fancier, where they don't reveal the intersection itself, but they do a little post-processing, and they reveal how many dollars did the customers spend, or how many customers saw it, not necessarily the individual customers themselves. And we'll see how to do this at the very end of the talk too. Another great example is like someone could be registered to vote in this upcoming election in more than one state. And that's actually illegal. It's only illegal if you vote in both states. But maybe you'd like to be able to identify these voters who may accidentally got registered in two states, and then see if they can be removed from one of them. And here again, for privacy reasons, you wouldn't want to reveal all the registered voters to either state. And so PSI can be used here. And maybe the most relevant application that we'll be looking at is known as contact discovery. So here, say we have some messaging app, in this case WhatsApp, and some new user signs up for WhatsApp. And what they'd like to do, currently their phone has a list of phone numbers of people they know, and they'd like to automatically have all their existing contacts imported into WhatsApp. But the problem here is that the cell phone itself doesn't know how to find, they just have a list of phone numbers. They don't know how to find them on the WhatsApp app themselves. And so currently one of the standard approaches, when a device signs up, they send all their contacts to the WhatsApp servers, and then the WhatsApp servers sends back the corresponding WhatsApp contacts. But then WhatsApp sort of sees who everyone's friends are or contacts are across the whole, like all of society almost, because even if you don't sign up for WhatsApp, maybe your friend does. And then now WhatsApp knows your information. And so to get around this, we can just run private set intersection, where only the phone would learn who are their WhatsApp contacts, and WhatsApp doesn't learn anything, at least initially. The core challenge in this scenario, and why many of the existing protocols don't work very well, is that the number of WhatsApp users is massive, maybe close to 1 billion. I'm not quite sure what their user numbers are, but we can say it's something like that. And while the phone only has, maybe 1,000 contacts. And so traditional, as we'll see later, traditional protocols require communication proportional to both sets. And so this ends up being a big problem if you want to actually deploy this, because phones aren't willing to download gigabytes worth of cryptographic protocol to be able to run this function. But we're far from the first. So here's a sort of history of PSI, and I really like private set intersection because there's such a diverse set of cryptographic primitives that have been used to construct PSI protocols. And here I'll go over some of the main general techniques. Some of the original protocols were based on Diffie-Hellman, and they somehow used Diffie-Hellman to create these pseudo-random values, which then are safe to compare and clear. Another line of work considered the observation that you can encode sets as polynomials, where each item is a root of the polynomial, and then you can sort of do polynomial operations to be able to compute a set intersection in some way. So there's been several works considering this. Of course, you can do generic secure computation, and surprisingly, even if you use garbled circuits, at least back in 2012, you actually get very good performance. This might not be the case anymore, but at least in 2012, even garbled circuits were competitive. But then sort of came along this idea of using this data structure known as a Bloom filter, which was a nice technique and still used in some settings. But definitely the most common approach has been techniques based on the cryptographic primitive of oblivious transfer. And this is where I'd say the most recent line of work has really focused. But we took a different approach, in that we started with fully homomorphic encryption as our sort of tool, our hammer, and we went and looked for PSI nails. And so we had a paper in 2017, and then another paper in 2018 that sort of improves and optimizes the protocol. So we'll be talking about these two PSI protocols. And then here is just a sampling of how many PSI papers there have been over the years that I've actually at least looked at. I'm sure there's many more. And so you can see it's a very rich area of research. Fun to work on. Okay, so back to our main application. Why is this scenario with asymmetric set sizes difficult to do using existing cryptographic techniques, apart from the FHE? Well, in this case, so here is a 1,000 mile view of how most PSI protocols work. So first, one party, in this case, WhatsApp servers, will sample a key, K, and then they'll run some sort of fancy cryptographic encoding protocol, where the other party inputs their set Y. And in return, they get an encoded version of all the elements in Y under that key K. How exactly this encoding works differs, but this is basically it. And then the WhatsApp side will encode their set X under this key K. And so you can think of F as just like a PRF if you want, or something like this. And then it's safe to simply send X prime, the encoded version of X, to the other party. And then they can locally intersect these two encoded sets and then map that back to the underlying items. And so basically, if all existing protocols first sample this key K and then encode the large set. And so whenever you do this, there's sort of fundamental limitations that this encoded large set has to be proportional in size to the original set. Yet, if we just consider, like, if you don't consider security, like, what could you do? Well, you could send a small set to the big set side, and then compute the intersection and send it back. And so clearly, we'd like to achieve something with communication complexity more proportional to this, which is proportional to the small set size. And the question is, can we achieve this? And considering that we've been talking about full homomorphic encryption for the last few days, everyone should know that in theory, yes, you can easily get communication complexity in proportion to the small set size. You just simply encrypt the small set size using full homomorphic encryption, send it to the server, and they compute the intersection and send it back. However, in practice, we all know that full homomorphic encryption can be difficult to work with if you're just running generic algorithms. In fact, they can be very slow. And so we'd like to get both a low communication complexity and good efficiency, so that, like, you could actually run this context discovery application in real world scenarios. And we almost achieve the minimum communication complexity, and we do get good computation. Yeah, I guess at this point, does anyone have questions? And then we're going to jump into some more techniques. I'll just continue if I see any. Okay, so first what we do is we're going to need a data structure known as a Cuckoo hash table, or Cuckoo hashing. And what this allows us to do, it's going to allow us to look up items into the constant time lookup, as we'll see. So say we have items Y1 through yn, and we'd like to construct a hash table so that we can find these items quickly. And what we'll do is we'll use some hash function h, and we'll get these hashes of each item. And then these hashes will point into the hash table. And then we'll stick Y1 at its corresponding location, and so forth. Pretty simple hash table so far. But eventually what will happen is that two items, in this case Y1 and Yn, will be mapped to the same hash table location. And there's various ways to take care of this. You can just store both of them there, but later we'll have reasons we don't want to store both here. And so we need to somehow resolve this collision between these two hash function items. So the way we do this is that we define a second hash function with H1 and H2. And when we get a collision, we evict the old item, and then we look at its new hash function location, or the second one, and that might land at some other collision. And we continue to evict the old one until eventually we'll get, hopefully, we'll get a configuration where there's exactly one item per bin. And you can show that if the number of bins is like 1.5 times the number of items, then using this this Cuckoo hashing technique will succeed with overwhelming probability and have one item per bin. And then we can ask, okay, we have some item X, and we want to see whether X is in the hash table. Well, it's pretty easy. We just look at the two locations that X gets mapped to. And if X is in the set of Y, then one of these two spots will hold it. So next, the next primitive that we need It's fully homomorphic encryption. I think everyone at this point is familiar. Just a few things I'd like to point out is that additions are very cheap. We don't almost consider them free, but multiplication is really, really where things get expensive. And not only is multiplication the expensive operation, but we're also depth limited because we actually don't use fully homomorphic encryption. We use somewhat or leveled homomorphic encryption. And so, so here, like if you want to multiply eight values together, you can form like a tree and do subsequent multiplications in a binary tree fashion. And so we'll be doing computations like this, but to achieve practical efficiency, we have to restrict ourselves to not go beyond depth 6, say. Of course, you can go beyond this, but then the number of multiplications we're going to be doing is like millions. And so if we do go much beyond 6, the performance, computation performance of doing all these multiplications will just be great. So we're really trying to, one of the main challenges is to describe a circuit which doesn't have high depth while still computing our set intersection function. Okay, so first thing I'm going to, as a warm up, we will consider the scenario where one party has Y and the other party has X, just single elements. And we want to check whether they equal to each other. This is sort of like a set intersection of size where the sets are size 1. And how might you do this? Well, first one of the parties will encrypt the element Y and send it over. And now a simple idea would be, okay, take Y and subtract X and send it back. And it's easy to see, at least for correctness, if Z equals 0, then that means X equals Y. It's pretty easy. But if it's not too hard to see that this also has security issues, and that the receiver can trivially recover the other item X just by undoing the computation. And so we need to somehow randomize Z. And the way we're going to do this is we're going to require that the plaintext space is some field, ZP. And then what we're going to do is sample a non-random or non-zero element R, and then we're going to multiply that with the difference of these two elements. And what we get is if X minus Y is 0, then this Z stays 0. Otherwise, multiplying by this R gives you a uniformly random element from that's non-zero. And so this perfectly hides, sort of information theoretically, the value of Y. And so yeah, that's a very sort of simple equality test. And then the question is, how can we extend this to a scenario where one party holds set X, or the sender holds a set X, and the receiver just holds one item Y? Well, we basically run the same protocol again, but instead of just subtracting one of the X values, we take the product of all the differences. And now, if any of the differences are, or if any X equals to Y, then one of these differences will be 0, and then the product will be 0 as before. And then again, we'll randomize the result so that we don't leak some sort of information on the set X. Great, this seems like we're making really good progress. However, there's sort of one issue here, is that if you recall, I said we can't go, our depth of our computation can't be very high. And say we have the set X has size big N, and they 2 to the power 28, close a quarter billion. And then this would mean the depth of this circuit to compute Z would be roughly depth 28, which is well beyond our sort of depth limit for practical performance, at least. So the first thing we will need to do to get around this is first sort of change how we're looking at this, and first observe that this computation, it can be written as just a normal polynomial as a function of X, set X. So we can just take the set X and then sort of expand it in its polynomial form to get these coefficients A1 or A0 through AN. and these are a function of x. And then we can simply do, evaluate the polynomial. But we haven't gotten around the issue in that we still need to compute y to the power n. And this, again, naively, if you just do the classic square multiply algorithm, or multiply add algorithm, I guess, would still require depth 28. So the next question is, how do we get around this issue? And we use a not too uncommon technique known as, I know as windowing. And here, right, our desire is to compute the power y to the n for some size of x, y. And the solution we just saw is, you multiply, you square, and then you can continue doing this and building up the power in the exponent. Another sort of trivial solution, a depth of 0 solution, is instead of sending y, we send all the powers of y. And then the sender can just simply pick out the one that he needs. But again, this has an issue is that your communication complexity is now proportional to the large set, which we want to avoid. And more generally, there's actually a smooth sort of spectrum between these two extremes. And the one we choose is you don't send all the powers, you send the log n powers, as shown here. And what this allows you to do is then you can take these powers of y and you can combine them to compute all the powers that you're interested in. And importantly, the depth of this circuit is log n. And so this is like basically a constant for us and definitely below our depth limit of 6. And an example of this is if we want to compute y to the power 7, we can just combine these 3 terms. And so if we had depth 28, now we have depth 5, which is depth bound. And the communication overhead is not too much. We only require now sending log n ciphertext, which is acceptable by our standards. So now let's take a look at our membership test. Instead of just sending y, we're going to send the powers of y, as shown here. And then we'll expand to get all the powers of y. And then we'll evaluate this polynomial. And since each individual a is known in the clear, these are basically, all these a multiplications are basically linear operations. And so the only like homomorphic, fully homomorphic operations that we need is when we are computing all the y's, expanding. And so we get the computational overhead is super proportional to the large set size, good depth, and good communication. And so it's great. So now if we have a protocol for testing whether a single element in the set y is in the large set x, we can simply repeat this protocol many times, right? That would be functionally correct at least. But the problem here is that if the small set size is little n, then we'd get quadratic overhead in terms of computation, which, if you have, say, 1,000 items on the small side and, 250 million on the other side, that quickly becomes impractical. And so the question is, how do we get around this sort of quadratic overhead? And this is where we are going to use cuckoo hashing. So here, the party with the small set size, y's, first constructs a cuckoo hash table, where at most one item is in any given bin. And then the sender will place each of his items at both hash function locations. So here you can see x1 is in the second bin and in the fourth bin, because that's the 2 locations that the hash function mapped it to. And so we have a guarantee that if some, say, yn equals x1, then yn will be in one of these 2 locations too. And so if we just do a membership test per bin, then we will get the final result that we desire. And if in the case when x is much larger, the size of x is much larger than the size of y, our sort of diagram would look more like this, where you have a single item and you're comparing it to roughly big N over little n other items. And so the overall complexity, when you repeat this protocol n times, is proportional to the large set size. So we just shaved off like a factor of 1,000 in terms of overhead. And so things are starting to look very good. And this is sort of our basic protocol, at least on an intuitive level. But we still have a lot of work to do if we want to get great performance. And the first thing we do, as I'm sure everyone has seen many times in this, is we apply this idea of FHE batching. And here, FHE ciphertext can actually support many plaintext slots in a single ciphertext. And so we simply take advantage of this, where instead of encrypting each Y individually, we encrypt them as a vector. And then we'll send that over and we'll do vector operations on each of the X columns. And so basically we're still running the same exact algorithm, but now we're doing this component-wise vector computation. And we check whether each slot of the resulting ciphertext Z is equal to 0. But one thing to notice here is that our communication going in one direction versus the other is sort of very asymmetric. And so the back communication is still of like sort of constant size, but our forward communication is log n. And so this raised the question is, can we sort of slightly increase the amount of communication that we send back, not more than the first message, but that will allow us again to decrease the depth and improve the computational performance. And so that's exactly what we do. We sort of split the big set X into S partitions. Then we run basically the same algorithm S times, S copies of it, and we send them all back. And so if you make S, say log big N, then your asymptotic communication has not increased. It's still proportional to the log of big set. And yet your depth of your circuit just decreased. And in particular, the depth of the circuit is now big N over, or log big N over little n times S. So if we in practice, this can get our depth now down to like 3, which is sort of wild when you think you're comparing, you know, 250 million items to one item. And then I'm not going to go into it here, but we also describe a maybe not too unstandard approach of that you can compress these back ciphertexts using some FHE techniques so that they get smaller. And this allows you to actually increase S a little bit more and get better performance. So it's a lot of combining all the tricks that we have in our toolbox that try to really optimize this protocol. And so what we end up with here at the end is sort of computation complexity proportional to a large set, good communication, and very small depth. And moreover, an interesting property of this is that, or I guess FHE in general, is that almost all the computation is being performed at this sort of large set size. So in the case of our contact discovery, this is some large server at WhatsApp data center. And while the cell phone is only doing encryption and decryption, so they perform almost no computational. Yeah, so there's a question on this previous, is how do you split information in X1 through X3, so into these splits? So before we just had a large data set. Here, in this case, when we run the sort of just the plain algorithm, we just have a large data set where we've represented things in these columns. And so when we do the split, it's sort of just arbitrary splits, and we just take the first, so many columns of X, and we batch them, sort of just logically put them together. And and then we just run the same algorithm several times. And so there's nothing sort of special about these splits. We just take the desired number of items per split and sort of logically group them together, and then just repeat the computation several times. And so, yeah, or you can just view it as like, you run the algorithm in parallel several times on subsets of the data set. But yeah, so each split is of equal size.
So Peter, a quick question. The fact that you're using cuckoo hashing,
Yes.
does it? Do you have to worry about leakage of information potentially? Because the hashing table might become full, and then sort of you need to sort of redo the hash table, and that depends on the data, right?
Yeah, you do have to be very careful when you're using cuckoo hashing, and there's two sort of avenues of leakage. One is if you fail to insert all the items, like you have some set which just happens to not cuckoo hash into this hash table for these given functions, hash functions. However, this problem can be gotten around by simply ensuring that the hash table is sufficiently large, such that with overwhelming probability for any hash function you choose, it will succeed. And so we simply sort of compute bounds on how large this hash table needs to be. And in practice, we find like 1.5 small n.
Okay.
The other source of leakage that you have to be careful of when using cuckoo hash table is that the position that an item ends up in is a function of the rest of the set.
Right.
And so if you can tell whether some item was in, if the party here with the large set can tell whether Y is in the first spot or in the second spot, that can leak information too. And so you have to be sort of careful about these two caveats. But here it ends up not mattering. Why can't you send multiple rounds of queries in case the items don't fit into the cuckoo hash table? In fact, you could do this. You could decrease, you could make your cuckoo hash table very, very compact, and then you have multiple copies of it. And in fact, one way to do this is instead of having proportional sort of n slots, you could have n over log n slots. And then you could repeat the protocol log times, where you just have multiple copies. And this is called simple hashing in PSI literature. But in the end, this actually gives you worse performance because you have to do so many replication, or you have to repeat the protocol so many times, like log n times, say, which in practice degrades performance. And so cuckoo hashing ends up being sort of the sweet spot where you get a compact hash table and you only have to run the protocol once. So now we're sort of moving on to our second paper, which considers, which ends up getting sort of better security against malicious parties. And while doing this, we actually end up getting better performance, sort of seriously. So first, let's consider the case when we have a malicious receiver. And the only thing that they do in this protocol is send encryptions of their input item Y. And here we're just doing the membership test for simplicity, where the receiver has a single item. And so pretty much the only option that the receiver has to cheat is somehow create bad ciphertext in some way. Maybe they're not powers, the correct powers, maybe the ciphertext are malformed, who knows. And of course, you could slap zero knowledge proofs on all these things, which might not be too bad, but would definitely decrease performance. Instead, we take a sort of different approach. So first, I'll need to introduce this idea of a PRF, OPRF protocol. And I kind of described this early on as this encoding function, but here's an explicit example of one of the encoding functions, OPRF protocol. And the the sender on the left samples a key K, and the receiver samples or inputs their item Y, and the key is input 2. And then the receiver gets output P or F with the key K evaluated on their item Y. And then using this OPRF, you can repeat this many times if you desire, with many Ys. And then a classic construction for private set intersection is then, as I sort of described earlier, is that you encode the large set X under the PRF key and send that over in a clear. And since the PRF sort of effectively randomizes all other values that aren't in the set Y, this leaks no information other than the intersection itself. But as I described earlier, the main issue for our setting, at least, with doing this protocol is that this second message is large, proportionally large. And so, but one nice advantage of this protocol is that if the OPRF protocol is malicious secure, as shown here in this case, then the overall protocol is malicious secure. So you sort of easily get malicious security when you're running a protocol with this paradigm. So we observed this and said, okay, can we just first run the OPRF protocol to sort of encode the plaintext sets X and Y into X hat and Y hat. And then we'll run our semi-honest PSI protocol on these encoded sets. And now you can ask, well, what if the receiver sends some bad ciphertext? Well, we don't really care, because instead of, we could have just sent the encoded set X hat in the clear to the receiver. And so no matter what function the receiver ends up making us compute, it doesn't matter, because it won't leak any information beyond this intersection itself due to the OPRF being first. And then at this point, you kind of, if you look at this long enough, you realize that this second protocol is actually just a form of peer. In fact, keyword peer, where the receiver has some element Y, and they want to look up whether Y is in some database X hat, and just check whether it's there. And so this is exactly the keyword peer primitive. And we just want to check whether X is in the database. And sort of at this point, we sort of like, wow, we actually created a peer protocol. We just didn't know. And so that's how we get malicious security against the receiver. And now we can move on to the case when we want malicious security against a sender. And here we don't quite get full security, but we get something reasonable. And since it's sort of inspired, since we're now using effectively a peer protocol to retrieve the items, we do something sort of curious. Instead of just having the encoded X hats, we encode them as pairs, key value pairs, where the key is X hat, and then the value is like a random oracle hash of X hat. Some complicated function H, but it will end up needing. And so now we perform peer on these keyword pairs. And if the Y is in the set X, then what we'll get out of the keyword peer is the hash of Y hat. Otherwise, we get sort of a didn't retrieve value. And so now the question is, how could a malicious sender cheat? Well, what they might do, one of the classic attacks is that they simply maybe make the receiver output their set. They always output everything. So the intersection is always everything. But now if you wanted to do this, it's actually quite difficult. So if we inline our protocol, again, get rid of the pure abstraction, say the malicious sender wants to force some Y to be in the output. Then what they need to do is they need to compute this hash function value, only given Y hat, or the powers of it. But since this computing, say SHA-256 on a FHE ciphertext is extremely difficult and requires a very high depth circuit. Even given these powers, it's very hard to compute, given just encryptions of Y hat, to compute SHA-256 of Y hat. And specifically, our FHE parameters are extremely small, where you only can perform a few multiplications before the ciphertext noise overruns it. And so typically we say that, it's sort of a bug that we can't do arbitrary depth computation using somewhat homomorphic encryption. But now we're going to use this sort of as a feature where it prevents the malicious sender from computing these hash values unless they actually know the underlying value, which is effectively means it's in their set. And so this effectively prevents the sender from just forcing the receiver to outputting a full set in the clear. It's the intuition. There's some caveats here, and we don't quite achieve like the normal notion of simulation-based security. But it's sort of an interesting idea, I thought. So the advantages of this sort of two-phase protocol is that we achieve this notion of malicious security. The second advantage that's not quite as obvious is that the first protocol actually required this notion of circuit privacy, where you have to flood the noise in the ciphertext before sending them back. But now we don't require circuit privacy because this X hat value can be considered public. And so we can use extremely bare bones FHE parameters. And this actually gives us better performance than if we hadn't run the OPRF protocol at all, much less even in the semi-honest setting. And sort of using this P abstraction, we kind of get a simpler interface. And then the final thing is that some OPRF protocols allow you to sample a key K once, and then you can encode many items. And so what, say in the WhatsApp scenarios, they would first pick a key K, and then encode their database once and for all under this PRF PK. And then they can just on demand run this interactive OPRF protocol with any client needed, which has small communication, and then run the peer part. And so the cost of running the OPRF ends up sort of disappearing in an amortized setting where you have many clients. The disadvantage is that now we have to run this first protocol, but that ends up not being very big.
Peter, which OPRF scheme do you use? Yeah,
so if you're going to run this protocol many times with many clients, it's best to use a DDH-based OPRF.
Right.
But if you're just going to run the protocol once, you can actually use a slightly weaker primitive and more efficient based on oblivious transfer, known as like a batched oblivious PRFs. And then you only need like symmetric key primitives for this.
Okay, so
depends. And then another extension that's sort of immediate is that now that we have, we're delivering labels like this hash function value as a label for our PR queries, we can actually stick extra data in there. So maybe, this is the public key of your friend that you're trying to retrieve from WhatsApp. And so you can simply check whether the hashes match, and then you can see their corresponding public key, or how you look them up in the WhatsApp scenario. And then a simple trick that I don't necessarily want to get into too much is that we can actually facilitate some sort of secret shared output, where for each peer, we mask the database with some random value R on each record. And then we can look at what we get as output. We get this value Z, which is the hash of Y XORed the value, or concatenated with the value, XORed this randomness. And so Z and R are now secret shares. And some sort of secondary MPC, you can check whether the hashes match and then recover the corresponding value. And so this way you can get, like, instead of computing the intersection, you can compute the sum of the values in the intersection. or something like that. And moreover, the communication complexity is still proportional to the small set times the size of the large set. And so this sort of gets us all our wide range of applications that we could then run. So wrapping up, here is a sort of diagram of the performance of our protocol. So over here on the right, we have several protocols. So these two at the bottom, ours is the green one with higher communication or running time, excuse me. And this is based on FHE and this like sort of FHE based peer. And you can see that it does achieve very low communication, but the computation to do like a real world size contact discovery, 5,000 versus 16 million requires, I think it's like 16 seconds, which could be parallelized on the server side. Another peer like PSI protocol is known as peer PSI, but this is a 2-server peer construction. And in this scenario, get 2-server peer can be implemented much more efficiently. And so you can see you get better running time, but their security model is significantly weaker. It requires like 2 non-colluding peer servers, which is sort of a unusual assumption in practice, versus ours achieves like a normal notion of security without any collusion assumptions. There are also several.
Peter, quick question.
Yeah.
Could you do have 2 parties here in this scenario, right? Could you imagine sort of implementing, letting them be the 2 servers in the peer protocol?
Yeah, the issue is that most of these 2-server peer protocols require both these 2 parties to hold the data set.
Right, exactly. Okay, all right.
And so it's sort of a chicken and egg because the client doesn't have the data set. So yeah, the 2 non-colluding servers each have a copy of WhatsApp's contacts.
I see.
WhatsApp users.
I see. So you're saying, so there are these protocols, like Boyle, Gilboa, Shai type protocols that use FSS more generally to do 2-party computation with small communication, right? But you're saying the communication is proportional to the sum of the input lengths as opposed to the min of the input lengths, which is in the FHE case, right? So you're really using the fact that one of the sets is small.
Yeah, exactly.
Could actually.
Yeah. And this peer PSI protocol actually does use that function secret sharing peer construction.
Okay. Okay. Cool. Thanks.
So yeah, in this blue range is where the low communication, sort of sublinear communication peer or PSI protocols are. And then you can see the result of having these other protocols up in this top range have sort of linear communication. And you can see that the communication complexity is here we're on a fast network, a LAN network, so you don't see the overhead of actually sending this data, especially if you consider like a cell phone. This is just pure running time versus communication. And so even though this like RA18 protocol is quite fast in terms of efficiency, they just sending the data in the end would end up blowing up the running time and sort of make it worse. And so that's shown here. And yeah, so that's sort of like the main difference. If you're willing to do linear overhead, then there's faster protocols. But if you need sublinear communication, then these FHE based protocols are the way to go, unless you can do non-collusion assumptions. And yeah, so that's I guess the takeaway. And I think the other takeaway is that if it takes 16 seconds on like a single thread server and only 16 megabytes, you could easily run this in like a WhatsApp scenario where you just and with an actual scenario, because like you'd only need to run this protocol maybe when you sign up for WhatsApp the first time and maybe occasionally afterwards. And so it's definitely practical. Signal was looking at this type of stuff, but they end up going with an SGX-based solution, or wrote about an SGX-based solution. And I thought they should have done this, but that's okay. Yeah, with that, that's everything. So thank you.
Thanks, Peter. So any more questions for Peter? So let me ask you something. So you mentioned SGX at the you mentioned sort of signal at the end. I happened to read the blog a few months ago, and I was thinking of sort of the same thing. Why not use this? So do you know why they went with the SGX, which I imagine is probably more efficient than PSI, right?
Yeah, it's definitely more communication efficient. I think they are asymptotically are still quadratic in computation, but it ends up not really showing up too much. I think one reason they did that is at the time of them writing that blog post, it was only our first protocol had just been released, and so there the performance wasn't quite as good, and it had some constraints in various places. And then we came out with this, and we talked to them a little, and they seemed like maybe the computational overhead is still a little bit large if you want to run it at global scale. I don't know. It's hard to say.
I see. So in the signal example, my phone would be the small set, right? I would have the small set, and
yeah. And in the signal example, what you do is you send the small set to the server SGX unit, and then in sort of batches, you run the full, or in a streaming fashion, you run the full server side data set through the SGX, and then you just record which ones ever match inside the enclave, and then
I see.
Send that back.
So I guess that would be of the order of maybe an order of magnitude, maybe 2 bigger than right. I mean, so it would be of the order.
Yeah, I think if you look at the pure PSI protocol, it is basically doing the same thing in terms of computational load, and so I think it'd be on order of this pure PSI, but they get one server.
Okay.
So you can see maybe that would give you an idea of the performance.
Yeah, one server, but trust, right?
Yeah.
Machine.
Yeah.
Okay.
I also heard they're might cancel SGX, so who knows?
Good. So yeah, if there are no other questions, let's thank Peter again. And Jessica Sorrell is our next speaker, and she'll speak in about 21 minutes at 12:15 Pacific. Thanks again, Peter.
Thank you.